Κύριε Πρόεδρε της Ακαδημίας, κύριε Ακαδημαϊκοί, dear friends, I want to welcome you, myself, in my turn, to this wonderful, timely summer school on behalf of Arcimedes AI, which is a new institute, which by coincidence is launching its operation today near Athens. It is the fruit of a very long dream, we have actually with us its scientific director, Timoselis, also, and I'll just spend a minute outlining what it is. It has three main goals. One is to offer to the outstanding Greek students the opportunity to have doctoral studies of world class in Greece. The second is to bring in touch the outstanding researchers in Greek universities in the field of artificial intelligence with the scientific diaspora in the same field. And the third one is to infuse in Greek society and Greece in general the fruits and teachings of this new technology. So, again, thank you very much for the invitation, and I have been deeply honored and humbled by the mention of the president of the academy to myself earlier. I'm going to give you a scientific talk about my work, my recent work, but let's start with. With a little story, and I know that many of you have seen this map. The story of AI is very peculiar. It starts with growth and progress, panic and decline, more growth, more progress, more hype, more winter, humiliation, and finally in 2013, takeoff. Okay, so this is the thumbnail sketch. And the question is, what happened in 2013? And what happened is that deep nets, the ANNs, an old idea, at least 15 years, in its germinal form, 50 years, 55 years old, finally worked. Okay, and the question is, why now? And there are four reasons, and I'm going to spend a minute. The first one is Moore's law. Every 10 years, we used to get a speed up of 100 in computer speed and all pertinent parameters. Moore's law is essentially dead. If it's not dead, it's on life support now, okay? But it delivered the AI with its last breath, essentially. The second one is that we have the internet now, and data are accessible and in massive form. And moreover, every time you send an email or you use online navigation, new data is generated, and you make AI even smarter, okay? So, and by the way, a huge bioethical problem here is that you never get paid, okay? So, and finally, it's a mathematical miracle that an old algorithm, which we have been overlooking for a long time, turns out to have the blessing of dimensionality, that when it works in 10 million dimensions, 10 million being the number of parameters that these deep nets have, at least, it works very well. as opposed to 3 dimensions. By the way, gradient descent is the simple algorithm that says, if you want to reach high, climb the steepest hill you see, okay? As you realize, if we're looking for Olympus here, okay, we will end up in Lycabettus for following this algorithm, right? I mean, but that's because we are in 3 dimensions. In millions of dimensions, things are incredibly much more favorable. Okay. And yet here is a fact. It turns out that artificial intelligence still lags far behind brains in several fronts, and groundedness. It lacks learning based on real-life world experience. Inventiveness and ingenuity, okay, you cannot create new things. Continual learning. Often, in order to learn a new task, AI has to forget the previous one. Emotional and social intelligence, that's obvious, I don't have to say anything else. And energy consumption. Your brain runs on 16 watts, okay? ChatGPT does not. It takes several jumbo jet flights between Athens and New York for it to be trained. Okay? By the way, how can I be sure? Why am I stating this as a fact? Because I learned it the old-fashioned tough cop way, okay? I interrogated AI until it confessed, okay? This is output from ChatGPT, okay? All right. So, here is an idea, and this is essentially my research agenda that I'm going to present to you. What if we started the AI from the beginning, but resolved, you see, as the president of IDEA said before, AI is inspired by the brain, but was inspired by the brain 60 years ago, when we knew next to nothing about the brain, okay? And got it completely wrong. I mean, at best, it is a terrible, inaccurate thumbnail sketch cartoon of the brain. And what if we develop from the beginning a new genre of AI, which is biologically plausible? It is brain-like, okay? For example, do not use backpropagation, the miraculous algorithm that I mentioned before, okay? In other words, what we want is to create a new AI that works like the brain works. And as soon as I say this, you realize that I'm in deep trouble, because we have no clue how the brain works. So just to illustrate, here is an incredibly massive work in cognitive neuroscience, and this is the standard reference for experimental neuroscience. And essentially, these are 2 colossal works of science, which are about the same subject, that essentially do not reference each other. Okay, so there is a huge gap. The gap is not just scale, 10 to the 11, but it is also a gap of scientific tradition, scientific methodology, and attitude. Okay, so these fields are very hard to put together to cooperate. And my Columbia colleague, Nobel laureate 2004, Richard Axel, said it better than anybody else. He said that we do not have a logic for the transformation of neural activity into thought. I view this, and then he went on to identify this problem, the bridging problem between these 2 disciplines, as the main open research question in neuroscience. And this is what I've been trying to do the last 10 years. Basically, what we want to do is we want to bridge spiky neurons and synapses with cognitive phenomena. And here is what my group is doing. We introduce a neural model, a mathematical model of the brain, and this model is very biorealistic, bioplausible. It models reasonably well spiky neurons and synapses, And with luck, we are going to implement through simulation complex cognitive phenomena. Okay, and this is what I'm going to tell you about. Is my goal clear? Okay, I'm insisting here because this is not a path that is traveled by many. Okay, you know what is most amazing about Axel's statement is that I seem to be the only one. I and my friends, we are the only ones who are doing this. So, what is NEMO? It's a mathematical model of the brain. I'm not going to explain to you, but I'll give you ways to find out more about it. But essentially, it contains brain areas. Each area contains, let's say, 1 million neurons. 1 million is a realistic number that we use in our simulations. There are random synaptic connections, very sparse, between these million neurons. And also, certain pairs of areas are also connected by very sparse random synaptic connections. We also have inhibition. Inhibition is inhibitive neurons are a vocal minority of our neurons in our brain, whose job is to keep it at 16 watts, okay? You know, in other words, they silence, they make sure that only very few neurons fire, and therefore you don't get epileptic seizures. So only a few, say 1,000 of the neurons, of the million neurons in each area fire at each step, and then you have Hebbian plasticity. If a neuron caused another neuron to fire, then the connection between them is, its strength is enhanced by, let's say, 5%. So this is the model and the parameters. The point is that now we have a state. The state is the neurons that fired in the previous step in each area and the weights of all synapses. And the next state is fully defined. And if you run NEMO, you can run NEMO because you can find the code online. It has emergent attractors. In other words, a behavior that is very stable and persistent. And this is called assemblies of neurons. And what are assemblies of neurons? Assemblies of neurons is something that we have been waiting for 75 years. Hebb, basically the founder of cognitive neuroscience, in 1949, my birthday, proposed that the way information is represented in the brain is through large set of neurons, which he called assemblies. For 55 years, we have been looking for assemblies, and only in the beginning of this century, technology advanced to a stage where we could find them. And for some time there was curiosity, but now there is, what are they? They are large and densely interconnected, stable sets of excitatory neurons in a brain area, whose near simultaneously firing is tantamount to the subject's thinking of a particular memory, concept, person, word, and so on. So, and now there is a growing consensus among neuroscientists that assemblies are the way the brain works. Okay, Buzaki, a major neuroscientist, he will get the Nobel Prize one of these days, calls them the alphabet of the brain. Okay. And if you are interested in technical details, there are 2 papers, one in PNAS and one in TACL, that contain them all. And here are my collaborators. The man on the right is essentially the architect of this software, my student at Columbia, Dan Mitropolsky. Okay. NEMO is capable of universal computation. Any computation you want to do, NEMO can do it. Okay? And by extension, our brain can do it. This is not an earth-shaking result, but it's reassuring. It would be remarkable if it was not, it would be sort of a defect if it was not correct. And also, it turns out that by suite of, let me say, clever technological computer science tricks, we are able to simulate NEMO on a laptop for a few seconds of brain time. Okay, so and we have GPUs, and we can simulate more extensive systems for longer. Okay, so we can simulate NEMO well, and it's enough to simulate a few Very interesting cognitive phenomena. And I'm going to, so remember the plan. Nemo models reasonably well the brain, and we want you to implement, okay, so this is a cognitive phenomenon. That's what I'm going to do next. And I'm going to talk about language, all right? I mean, so I don't need to tell you, language is sort of, an incredible feat that every human can do. And it's a miracle, okay? So, right now I'm creating sound waves in our space, and these waves eventually reach your medial temporal lobe, and there they become hierarchies of assemblies, okay? And if I'm very lucky, you are going to remember these hierarchies as long as you live, okay? So, why I find it a very interesting subject is because it's not just any feature of humans. It is the last feature to humans, okay? It developed for the last 3,000 generations, while our brain has been the same, okay? There have been no major brain mutations the last 3,000 generations. And as a result, it must be a mirror of the brain that mothers change the language they talk to their daughters by making it easier for human brains to learn it, okay? So this is the reason why I believe that it should be a prime subject. And as a first step, 3 years ago, we created a parser of English. Parsing is what we are doing right now. You hear a sequence of words and you put them together in hierarchies. In other words, you hear a sequence of words, okay? So you is the subject, here is the verb, sequence is the object, of words is, and so on, prepositional, and so on. All right. And the architecture of the parser is all these brain areas, fibers connecting them, and all these labels. Lex is the lexicon containing the words, an assembly for each word. And when you hear a sentence, this machine gets into work, and we make sure that it gets you the right parse, create the right architecture. And it very closely mirrors what we know happens, or we believe we know happens in the brain. So let me go quickly, but so I think I'm going, in the interest of time, I would just mention this. This parser, these are actually questions that we often encounter. This parser is not competing with other amazing parsers that deep learning produces, okay? Its point is that it is biologically plausible, okay? It's the first of its kind. And by the way, we don't know that it cannot become as good or better, okay? Number two, this is not a theory of how of parsing happens in humans. This is essentially a proof of concept, okay? But we have tried to make it compatible with a few things that we know about how parsing is done in the human brain. And finally, what is most annoying of all is that we assume that all these mechanisms, all this apparatus is in place, okay? And the question is, how do babies fill the blanks? Okay, this is a fair question. And when the baby is born, it has this. Okay, how does it fill the blanks? Okay, and how about semantics? In other words, parsing is one part. Okay, you find the syntactic, the superficial structure of the sentence. What is the meaning of the sentence? What does it mean for you, for your life? Okay, that's a separate question. How about generation? The baby eventually has to learn how to speak. So what I'm going to talk next is essentially, to put it in a sensationalistic way, we are creating an artificial baby that can be taught language, okay, can be taught to speak. Okay, so here is what I mean. We are creating a neural tabula rasa, which, when you give it a modest input of grounded language, what is grounded? Grounded means that it is presented in the context of something happening in the world, okay? With shared attention, this means that the tutor and the pupil are looking at the same thing at the same time. We learn to comprehend, means understand and to generate sentences in the same language. Okay, so this is what, and of course it has to be independent of language. Okay, so is this clear? This is our goal. And we are making significant progress, as I'm going to tell you. For example, here is how representation works in our system. There is a lexicon for nouns, okay? Psycholinguists basically agree that nouns and verbs are stored in separate places. And for example, the noun dog is there. It's deeply rooted in its phonetic representation. We assume that phonetics has been solved. You know, this is something that we don't want to. And then it is solidly rooted in vision. Okay, that every noun, especially every object noun like dog, has a visual representation which is its primary semantic content. But of course, it has other. It may have olfactory, motor. You have a sense of how dogs move. You have affect. You have feelings for dogs, either fear or love or both. Okay, so this is how we represent in our system. And the arrows, the two-sided arrows, they are synaptic connections, strong synaptics, strong connections. The strength is denoted by the width of the line between connecting them to the root, to the symbol dog. And a similar thing happens for verbs. This is a representation of the verb crawl, and this one is most strongly rooted into motor, because that is what verbs, where verbs are known to pertain to, to connect to in the human brain. Okay, so we ran an experiment with this. We created this system and we taught it language, and it worked. Okay, it spoke. Okay, so the only difference is that for now we only have intransitive verbs like run and jump. Okay, so there is there are chase and jump. Okay, so two-word sentences like doggy runs, and we solved the hard case. Nowadays parents teach their children language by doing, of course, speaking to them, but also doing individual word tutoring. Okay, doggy runs. Okay, so and that's of course commendable because it makes a lot of difference, but that's not the hard case. We know that children can learn from overhearing sentences. Okay, we know this. How do we know? For example, okay, in the primitive village where your ancestors lived, I doubt that the women in the village, the men were hunting, away hunting, were very busy surviving, and they probably did not have the time to do. So they were just chatting with each other, and that's the children, I believe. Okay, so I can only presume. That's how children learn how to speak. And the other one is migrant children. Okay, they come to America or Greece. Okay, so at home they don't speak. Nobody speaks the language. At school they are probably despised and bullied, and yet in 2 months they learn to speak decent English. Okay, and this is the miracle. Okay, that we want to reproduce if they are in the critical period. So basically, we want to reproduce the first 2 years of the baby's life, where the sort of the culmination of this language school is that the baby finally says something like "Daddy left." Okay, so a two-word sentence. Okay, this is a byword. This is sort of, it happens at between 20 to 24 months. So we must create. So basically, we feed the system sentences like doggy runs, deer jumps, horse eats. Okay, and we want to create for each word a representation in the correct area, okay? The nouns go to the nouns area and the verbs goes to the verb area. And that's very difficult. And the reason is, what's the difficulty? That we don't know if this is English or Irish. If doggy runs is in Irish, then doggy is the verb, okay? In English, doggy is the noun. You see, Irish has verb first. And all languages have all different word orders, and some of them are very rigid. So that's the difficulty. If you are a computer scientist, you realize that this is a very difficult problem to solve, and you can solve it. And here is the experiment. We solve it obviously for the things we can simulate in a linear number of sentences. Grows linearly with lexicon size. Okay, so so we went up to 20 verbs and 20 nouns, and after 250 sentences, always the child has created an appropriately partitioned lexicon, and it can generate sentences on its own. And single word tutoring helps. Okay, so the blue curve is when you very often do single word tutoring. The other curves is when you rarely or never do single word tutoring, and you can see that this makes language learning easier. And what are our next challenges? And I'm finishing. We want to do generation. This we have done already. Okay, so the baby learns elementary syntax, is able to generate something like dog eats. Okay, to scale it to 100 words, that's a tough one. We will need more computing power, but we have ideas on how to do it. We don't want to go far beyond that now. Probably we'll leave it for others. But 100 words is about what a 2-year-old knows. Okay. About 100 words. Multilinguality, you know how to do. Okay? As you know, many babies grow bilingual, and of course we learn, and we can't do multilinguality. In other words, our representation system can very easily handle bilingual language acquisition. Transitive verbs and object category. Okay, that will be a challenge, but we sort of know how to do it. Abstract words. Okay, so that are not rooted in vision and action, like peace and contemplate, okay? There are psycholinguistic theories that I think we know how to implement for this. And finally, this is our major thing, subtleties of syntax. Syntax, language is a very complicated thing, and we are looking forward to finding obstacles that we cannot conquer. And as a result, we'll have to change and enrich our model. Okay, this probably will happen sometime in the next year. Okay, so to conclude, the study of the brain is the most fascinating and the hardest thing I've ever done. Okay, so it's the steepest hill I've ever climbed, and this is just the beginning. Okay, so we have a lot places to go, and what is despite, in addition to being a very fascinating subject, what this gives us, it brings us in touch with some of the most profound questions about ourselves. Okay, so how language is implemented, because the thing that we're trying to duplicate is an ancient question. Okay, we have made progress in biologically plausible acquisition, and with this, important question: is Nemo what Axel was thinking about? Okay, so I've talked to him. And it's still, he's still trying to decide. Is the design of neuromorphic simulated intelligence systems like Nemo a useful complementary path to AI? And with this, thank you very much.